In this lecture, we're going to see how to use the Numpy library to help us implement the Needleman-Wunsch algorithm for alignment. So I'm going to start to talk a bit about namespaces in Python and the import instruction. And then we're going to see how the Numpy library makes it easier to do matrix operations. In theory, we could do this with lists and lists of lists, but this makes it a lot easier to do the operations to compute the scores matrix. And so we're going to use Numpy to implement the global alignment algorithm. And then we're going to see a bit about the exercise that you're going to do, which is to implement this sequence alignment algorithm. So let's start with the namespaces and the scope of the different names in Python. We can think of a namespace in Python as a directory or dictionary where the interpreter is storing which names are valid and which values they correspond to. And there are different namespaces, there are different tables, so to speak, with these names for the purpose of preventing name collisions. Such as having different functions using the same name, or different functions using the same variable, or functions that may have the same name but are used differently in different contexts. So basically the namespace determines in a given context what the name refers to. There are some basic keywords that Python has, such as for, def, if, and so on, that are always valid and always mean the same in all namespaces. But then we already saw some names of objects that only exist in specific namespaces. For example, imagine that we have this string, AB, CD, and we call the split function to split by the comma. If we just write a split function like this, we get an error because this does not exist. Python does not know what this name split refers to. But if we say that is s.split, that is the method split belonging inside the namespace of a string object, then we can use it to split the string stored in s. So this split here inside the string namespace exists, but the split here outside does not exist. So this is one example we already saw before of the namespace, different namespaces and the object existing in only one of these namespaces. Python looks for the names in order, first in the local namespace, then the enclosed namespace. This can happen when you have functions defined inside other functions or inside classes and so on. We are probably not going to see many examples of this. Then the global namespace, which is the names defined in the same module, and then the built-in namespace, which is the namespace for reserved words like def and print and things like that, that are always defined in this outermost space. So this is the order Python follows, and this is why you can write a function that can access variables outside the function, but when you create variables inside the function, these are not accessible outside the function. So for example here, if I create this function will print var1, and var1 exists in the global namespace. So we can think of what Python is doing here, which is first looking up in the local namespace of this function, and it doesn't find any var1. So it goes to look, along this list. Eventually it looks in the global namespace and it finds this meaning for var1, which is it points to this string here, I am global. And so when we run this function, we call this function, it will print I am global first, and then I am local, which is var2. But if we try to access var2, we cannot find it, because note that in this context we are only going to look here in the global and the built-in namespaces, so we cannot find var2. We don't have access to the private namespace that is local to this function. So even if we change the value stored in var1, we change what the function is doing, because now when we call the function, it will go look for var1 and it will use this value. But if we change var2, if we create a global variable var2 here in this namespace, it does not affect this one here. This one is still the local one inside the function. So this is another example that we already saw, the different namespaces, and this is one of the things that guarantees that functions can be then used to solve sub-problems and combine all the different problems into the problem we're trying to solve without having some undue interference, because each function has its local namespace. But something that we can also do here is to import names from different modules. In Python, a module is a file with the Python source code. So suppose we have this solution for the reverse complement exercise we did last week. So we have here a function that computes the complement of a nucleotide, and what it does is going to look at the position of the nucleotide in this global variable base, and then it's going to use the character in the complement that corresponds to that position. So if this is an A here in N, it will find this in the position 0, and so it will return the position 0 of comp, which is this T here, and so on. So basically this is one way of doing the translation between each nucleotide and its complement, and we create two variables here, global variables. By the way, this is one notation that is often used. If you have a variable that is not going to change, its value is constant in your program, you can write it in uppercase, and this indicates that this is a constant and it will not be changed by the program. And it's useful to store this kind of information. So now we're going to look at these variables here, because since these names do not exist in the local namespace of this function, Python will look in the global namespace of the module, which is this file, and it finds the variables there. Okay, so this gives us the complement of one nucleotide. The complement of a sequence is we start with an empty string, and now for each element of each nucleotide in the sequence, we get the complement of that and add it to the string. So now we keep growing the string like this, and we return the complement. If we want the reverse complement, then we just call the complement function and we return the string, but in inverse order. This is a slice that is going from the beginning to the end of the string, but with a step of -1. So it's actually going from the end to the beginning and reversing the order. So suppose we have this implemented in this file, refcomp.py, and we want to use, for example, this function for computing the reverse complement. We can easily do this without having to execute the whole script, because this is what we've been doing so far. We write the script, we execute with F5 or in the play button. But in Python, we can import the modules. So what we can do is import, for example, this module, and if the code that we have here is saved in this file, refcomp.py, in our current working folder, we can do this, import refcomp, use the name of the file without the extension, and what the interpreter will do is run that module. So it declares, as it runs the module, it creates all of these objects, but imports into this context that we have here, into this namespace, the name of the module as an object. So this refcomp is an object that has all the functions that exist in the module. So we can call from the module refcomp the reverse complement function, apply it to some DNA sequence, and get the reverse complement. Note that in this case we are importing the module itself as an object into our namespace. So we cannot call reverse complement like this, because reverse complement is something that exists inside the namespace of the module and not here in our namespace like this. However, if we only want this function, we can do it like this. Instead of importing the whole module, we can say that from this module we're going to import the function that we want. And now we import this name into our namespace, and we can use the function as if we had run the module here or something like that. So this way it's easy to write code into different modules and then reuse codes that you want. Another thing that you can do is to import a module but give it a new name. So I'm going to import this module, revcomp, it's the name of the file, but I'm going to give it an alias which is this rc. Now I don't have to write revcomp, I write rc, this is the name of this module in this namespace, and I can access everything that exists inside of the module. So this not only works for modules that you have in the current folder, but also for modules that are installed in libraries. And this will be most of the cases we're going to use. And one of them is this Numpy library that we're going to use. So you can use lists to hold multidimensional arrays. For example, we can create a list of two elements in which the first element is a list and the second element is a list of the same size. And the meaning of this can be a matrix that has two rows. So this is what we are trying to represent here. We are trying to represent this matrix. So one element is one row, the other element is the other row. If we want to access a row from this, we can access the first element of A, because the first element of A, for example, is the first row. The second element would be the second row. If we want a specific number here, specific cell in this matrix, we can say, for example, from A, the first element of index 0, and from that one, the element of index 2. And in this case, it's this 3 here, because this is the element of index 0 of A, and this is the element of index 2 of A0, which is this list here. However, this is not very practical, both for doing computations and matrix operations and so on, and also for the way that we have to index the cells in the matrix. Lists are very good data structures for appending elements. In fact, they are optimized for that. So if you create a list and you append elements to the list, this is done very fast in Python. For example, this solution here is actually quite inefficient in Python. When you do something like this, adding a new element to a string and then putting that again in the same variable, this requires creating a new string with this concatenation, copying everything there, and then replacing what we had at the beginning. So this can be very slow if you have very large strings, whereas the append method on lists is very fast, because the list is optimized to simply at the end point to the new element and chain all the elements together. So lists are good if you want to grow them by appending new things, but they are not very practical if you want to do matrix operations. So for that, we're going to use the Numpy arrays. We generally will import the Numpy module as this alias np, so that we don't have to write Numpy all the time. And this you'll see in many examples. If you look on the internet for examples on using Numpy, this is what you'll often see, this way of importing it. We have different functions here in Numpy to create matrices and vectors. This actually can store n-dimensional arrays, so you can have a one-dimensional vector, a two-dimensional matrix, a three-dimensional tensor, and so on. You can have things with any dimensions you want, and you specify the dimensions, for example, in the ones or zeros methods here with tuples, or just an integer if you want a vector with only one dimension. For example, ones 5 is a vector of 5 ones, zeros 5 by 5, in this case using a tuple here, creates a matrix of 5 rows and 5 columns. you can also create an array, an NumPy array from lists of lists. So in this case, this is a matrix with 2 rows, and each row has 3 columns. If all of these have the same size, then this works perfectly, and you get an array representing the matrix. The advantage of using this data structure, the NumPy array, is that it gives you lots of functionalities. Some are just informative. You can have you can check the type of numbers that are stored there, or ask for the shape. For example, if you have this matrix here, this would be a matrix of 3 rows, each one with 2 columns. And if you create the corresponding array from this list of lists, you get a matrix that has this shape, 3 by 2, 3 rows by 2 columns. But the most useful thing about this data structure, the NumPy arrays, is the way you can index and broadcast operations using these matrices. For example, suppose that we create this matrix here. This is a matrix with 3 rows. Each row has 4 columns and has these values, 1, 2, 3, 4, all the way to 12. If we ask for this matrix divided by 2, NumPy will broadcast this operation through all the elements and give you a matrix where each element has been divided by 2. You can, for example, add 5, and it does this to all the elements. And if you do an operation with an array of elements, for example, a list or a NumPy array, if NumPy will match this array with the last dimensions of the matrix that you have here. So in this case, these would be the columns, these 4 elements, because our matrix has 4 columns, and then it will broadcast through the rest of the dimensions, so in this case through the rows. So this means that for each row in your matrix, you are adding this array, which is add 5 to the first element, add 10 to the second element, 15 to the third, and so on. So since the first element was 1, we add 5 and we get 6 there. The second element was 2, we add 10, so we get 12, and so on. And then this is repeated for the second row, which has 5, 6, 7, 8, so we get these values here when we add each of these in order to each of those in the second row, and then the same for the third row. So this is one very useful feature of these objects, because it allows us to vectorize, to distribute these or broadcast these operations through the whole matrix in a single instruction. We don't have to do many loops and things like that in order to repeat the operation. Another useful thing is the way these aggregations that are implemented in these objects. So NumPy has these functions, sum, mean, standard deviation, max, and so on, that we can apply to these objects and get the results, the mean of all the values in the matrix, which is even more useful if we specify an axis. So if we do, for example, the sum of the matrix, it sums all the elements in the matrix. The mean is the mean for all the elements. But if we specify an axis, for example, the maximum with axis 0, it's going to compute the maximum in the direction of the first dimension of the matrix, which are the rows. So it's going down the rows, and it's going to compute the maximum for each column. Or the sum, for example, going along the columns, it's going to compute the sum for each row. This 10 here would be the sum of these elements, the 26 is the sum of these, and so forth. So by doing this, we can aggregate elements of the matrix along a specified axis. Now here we are finding something that we never saw before, which is putting these names in the arguments of the functions. So just to talk a bit about this, you can have functions with default values. If in the parameters you assign some value to the different parameters. For example, in this case, we have this test size function that receives a number, and has this minimum value with the default value of 1 and this max val with the default value of 10. And then it compares the number with the max val and the min val and returns different strings. If we call it like this, test size 5, then number will be 5 and the other two will be 1 and 10 respectively. If we call it like this, for example 5, 6, then this 6 will be used for the second parameter, which is min val. So in this case, the result will no longer be minimum, it will be small, no longer will be medium, but it will be small because now this condition will be verified. Min val will be 6, and since 5 is smaller than min val, then the function returns this value. Or we can include also this last argument here, and so in this case 514, the number will be 5, min val will be 1, max val will be 4, so you will have this condition true and the function returns large. When we have several default values, it may be useful to omit some that we don't want. For example, suppose that we only want to specify the number and the max val. We want to keep min val in default. For that, we can pass argument by name. For example, here we have 15 on the number. We don't do anything on the min val, but we say that max val is 20. Once we give a name here in the arguments, it must be the name of a parameter, then the argument value will be stored in that parameter. And we can do it like this. We can specify everything by name, and if we specify by name we don't need to worry about the order. But this is often useful when you have several parameters with default values and you want to send arguments only for a select few of them. And this is what we are doing here. We have several parameters for these functions, but we only want to specify the axis one. We can leave the rest on default. And you have different, in Python functions, this often happens that you have a number of parameters that have default values, and you can choose which ones you want to send arguments to. Another useful thing is the way we can index these arrays. Not only can we use both dimensions here in indexing. For example, this first part refers to the rows of the matrix, and this second part to the columns. But we can also use Boolean values for indexing our Numpy arrays. For example, I have here this matrix, and then I'm going to create this vector 1, 2, 3, and I'm going to compare the vector with 1. When I compare the vector with 1, this operation will be broadcast into 1, 2, 3, and it will return an array of Boolean values with false, true, true, because for 1 this is not true, it's not greater than 1, but for 2 and 3 it's true, they are greater than 1. So we have false here, true here, and true here. But now, since this array of Boolean values has the same number of elements as the number of rows in this matrix, I can use this array for indexing the rows of the matrix. So now I only get the rows of the matrix that correspond to true values in the array. And this column here means that I want all the columns for each of these rows. I could also add other constraints here, say only the 2 last columns or something like that. I could do something like this, for example, the 2 last columns, or the first 2 columns, whatever I wanted here. This makes it easier to index the different elements of the matrix. Okay, so let's see here an example. We're going to compute the diameter of a protein. This would be the example I'm going to use. This is the sulforedoxin from the Sulfovibrio gigas. You can find this structure in the protein data bank if you want to look it up. but we are not going to worry now about these protein data bank structures and so on. I'm going to talk a bit about that in the introduction to structural bioinformatics at the end of the semester. But for now, let's say that we have all the coordinates of these atoms in a file called protein.py, and this module defines one variable, which is a list of tuples, and these tuples are the coordinates of the atoms. It has about 520 atoms, this protein. So these are the coordinates. These the values here are in angstrom, and what we want to do in our problem is to compute the diameter of the protein. We're going to find the longest distance between any pair of atoms here. So basically, we're going to look for the atoms that are furthest apart, and this would give us the diameter of the protein, the largest length of the protein here. So we can decompose the problem if we use it with this data structure here. We can start by computing the distance between 2 points. We can create a function for that. Then we take 1 point here and we compute the distance to all of the other points, keeping the largest one, and this will give us the largest distance between 1 point and all the others. And now we're going to repeat that for all the different points, so that would be another function, and get the largest distance between all pairs. So if we decompose like this, we can solve the simple problems first, and then go complicate a bit more, and then bring everything together. So let's do this first without Numpy, just with these lists. We receive 2 tuples here for 2 points, which are the atom coordinates, and we output the distance between them in 3 dimensions. Then we have this max distance function, which receives the coordinates for all the points and 1 reference point, and it computes the distance, the longest distance between any of these points and the reference. So it's going to measure the distance between all of these and the reference point and return the longest one. And now for the diameter, we're going to get this longest distance for all the points as references and return get the distance for all the points as references and return the longest one. So this way we avoid having to do many for loops nested inside one another, and this is just the outline of the program. It's a good idea for you to think about the program first and just write what functions you're going to need, and then you can focus on implementing each of the functions. So for example, we start with this one, the distance between 2 points. The points are in 3 dimensions, so these would be either tuples or lists with 3 coordinates. We can unpack each of them into 3 variables, x1 and x2, y1 and y2, and so on. And now we just use the expression for Euclidean distance. We are going to square the differences of the coordinates, sum everything up, and then compute the square root of this total. And this will be the Euclidean distance. And now we can check if this is correct for different pairs of points for which we know the distance. Now we can go for the next one, which is getting the maximum distance between an array of points and 1 reference point. So this would be the algorithm. We start with 0 because we know that there cannot be a distance that is smaller than 0. And now for each point in the array, we compute the distance to the reference and replace our maximum distance if the distance found is greater. Once we reach the end of the loop, we have the longest distance. So this is the idea here. We start with max d at 0. For each point in these coordinates, for each c in these coordinates, we compute the distance to the reference point and check if this distance is greater than the maximum so far. If it is, we replace the maximum, and so at the end of the loop, the max d value will be the largest of all the distances we found between the points in this list and the reference point. And now we can test this. We create a list of points, for example this one, and now we compute the maximum distance to the origin of the coordinates, and this should be the point that is furthest away is this one, 0, 0, 10, and the distance should be 10. So we can check if the result is correct. It's important to always check if your functions are working before going on to the next one, because since they are using the previous functions, if you don't check this step by step and you find an error only when you're using everything at the end, then it's much harder to figure out where the error occurred. And now we can end with the final function to compute the diameter of the protein. So this could be a first version where we do something that is similar to what we did here. So here we are looping through each point in the coordinates array and measuring the distance to the reference. And now here we are going to loop through each point in the list of coordinates of all atoms, use that one as a reference, and obtain the maximum distance to all the other points using this max distance function that we created here. And once again, we start with 0 and we update if it's greater, and so at the end we get the maximum distance between any point and all the other points, and this would be the diameter for the protein. And we can test this with the sulforedoxin and check the result. This is about 30 angstrom. But the problem with this implementation here is that it duplicates computations. So when we use point I as the reference, we are measuring distances to all the other points, including point J. And then when we use point J as a reference, we measure distances to all other points, and this includes point I too. So we are measuring the distance, the same distance in both ways, and we are doing twice the computations necessary. So we can improve this a bit. We're going to consider that the reference points are only going from the first point to the one before the last, and then we are going to compute the max distance only to the points that come after the reference point. So if the reference point is index IX, we are going to measure the distance only to the points in our list of coordinates starting from the next one to the end. And we do the same thing, check if the distance is greater than the maximum, and so on. But this way we avoid repeating the comparisons between point I and J and then point J and I. So this would be an improved version that does fewer computations. Okay, so this is how we could solve this problem without using Numpy, using only these lists and doing all of these things step by step with loops. If we use the Numpy array, we can have a greatly simplified code. So we have this diameter function that receives the coordinates, and we create a matrix from these coordinates. So remember that the coordinates are a list of tuples, but when we use this in the Numpy array function, we now get this array object that has these additional properties that we can use, for example, indexing the rows and the columns. If we create a matrix like this with lists of lists or lists of tuples, then we can only index in this way. First we specify the row, then we specify the column. With the Numpy array, we have this more elegant way of indexing the positions, and we also have the ability to broadcast operations. So what we can do here is we start with the diameter of 0, the maximum distance, and now we go from we loop through the rows, or the index of the rows, starting from 0 and all the way to the row one before last in the matrix. So this is the shape of the matrix is the number of rows here, the shape, the first element of the shape array, and this -1 is the number of rows minus 1. So we can use each of these as reference and compare with everything that comes after this row. So let's store here on the reference the coordinates on this row, and we can do that by using from the matrix the row with this index and all the columns. This gives us the 3 xyz values for these coordinates. And then we can compute a vector with the distances by adding the difference between the coordinates of all of these points, the ones starting from the next row all the way to the end, and the reference point. So this is one point. This is a potentially large number of points, but this operation is broadcast, and so this is subtracted from each of the points in this part of the matrix. And so here we get a matrix of dimension n times 3 with all the differences in the coordinates. We compute the square of each difference of these coordinates. So we again get a matrix of n times 3 with all these squares. And now we sum it so we add all the elements along the columns. And this gives us the square of the distance between each of these points and the reference. And now when we compute the square root of this array, we get an array with all the distances between the reference and all the points that come after the reference point. So they start at row plus 1 all the way to the end. Now we can get the maximum using the max function from Numpy. And now we can check if this new maximum distance is greater than the diameter so far. So you see that all those, the individual computation of distances, the first loop for the maximum and so on, we can avoid that and just write a single expression, which is from this matrix of coordinates, subtract the reference point from all of them, compute the square of all the differences in the coordinates, add this along the columns so that we have the sum for each of the points, and then compute the square root to get the distance. So here we get a vector with all the distances. Okay, so you're going to do this exercise as a tutorial, check the different values and see if you can understand the different steps, because now using this Numpy array, it's a lot easier to create those matrices that we need for the Needleman-Wunsch algorithm and global alignment. And this would be the exercise that you're going to do. So I'm going to help you a bit with the decomposition. We can start by creating a function for the substitution matrix. It can be simply +1 if the symbols are equal, -1 if they are different. So this could be match, nucleotide 1, nucleotide 2, and it returns the score. Note that I'm not writing the actual function here, so you would have to do something if n1, for example, if n1 is equal to n2, then something, and so on. Okay, so you would have to write the function yourself. I'm just showing the outline of the program to help you with this decomposition part, because implementing the function is an exercise to see if you really understand the Needleman-Wunsch algorithm. Now we're going to create a function for the global alignment that's going to create two matrices. One with the scores, and this is the one that we saw how to compute. So you start with the gap penalty. So this function receives the sequence 1, which will be here on the rows, sequence 2 on the columns, and then the gap penalty. So we start by filling this matrix with, for example, you can create this matrix with zeros. You can use the Numpy zeros function here. So basically one thing you can do is the scores matrix is the Numpy zeros with the size that is the length of S1 plus 1. This is the number of rows, and the length of S2 plus 1 as the number of columns. So this could be the dimensions of your scores matrix. The same for the moves matrix. You can use the same dimension. And so this will create the matrix, and then you need to fill in these values on the first row and on the first column, which are the ones where we have the gap, because on the first row we are skipping elements of so using elements of the top sequence and just aligning them with the gaps, and on the first column we are doing that with the first sequence, the one here on the right. So this would be one of the matrices the function here will return, which is the matrix with the alignment scores, the one that we're going to fill with dynamic programming. The other matrix that is useful to compute here is the one storing the different moves. So, for example, going into this cell, we are moving from here into here by matching the first element in the sequence. I'm not showing the sequence here, but let's pretend that we have a match. So that's why we have a score of 1 here. And if we went, say, from here to here and then down, we would have -4. Going from here, from the beginning down and then right, we would have -4 too. So out of the 3, the highest score is the match going in the diagonal. And so we can specify the move there by indicating the diagonal here. So this could be 2 indicates a diagonal, 1 indicates moving to the right, or yes, to the right here. So this could be ones over here, and 0 can indicate moving down. This first one doesn't matter. You can leave there anything that you want. Sorry. So this first location is not important, but all the others will have the directions you came into each cell, because then they will allow you to trace back. Note that the first location doesn't matter, because when you reach that one, you stop the backtrace, because now you used up all the elements in the sequences. So you can do it like this. For example, 0 is down, 1 is right, 2 is the diagonal. And then you create the moves matrix with indicating the directions that you're coming. This is arbitrary. You can choose whatever values you want, but these would be the 2 matrices that the global matrix function will return. Scores, so that we know the score and we can compute all the moves, and moves so that we can then do the backtrace and create the alignment. And another detail here is that we're going to receive the match function here, which will be a function like this one that we're going to call to get the score of matching 2 residues, 2 nucleotides in this case. Since we may want to change, to use different substitution matrices, we can create several functions like this, and then just choose which one to send into the global matrix function. And this is something that you can do easily in Python, because you can receive, for example, I create here a function 1 that does something and returns some result. And then I create a function 2 that uses some function to compute some intermediate result here. And I can call function 2, giving whatever arguments I need for those parameters, and then giving function 1 as an argument to this parameter. So since I don't have parentheses here, I'm just giving a reference to this function. So it's like the handle that Python can use to call that function. So this is what is going to enter in this parameter, is just the object of the function. And inside this function 2, that function can be executed putting the parameters after the name. So in this case, function 1 means this function here. This is passed on to this parameter, and inside function 2, when this sum function is called, this refers in this case to function 1, so this one is executed here when Python finds the parameters. The important thing is that we do not put the parameters here, so that Python just passes a reference to this function here and does not try to execute it at this stage in order to pass the result. We don't want to pass the result, we want to pass the function object so that this one can use it. And this is the way you can make it so that the global matrix function can receive any function that returns the substitution matrix, and we don't have to worry about which one we're going to use at the time we are implementing this one. Only when we call it, we decide which function to use. So now we need to write the traceback function. This one will receive the two sequences and the moves matrix that we produced previously. This one that indicates the different directions that we're going to move. So now what we're going to do is to use these two sequences and the different moves to create the two alignment strings. These are basically the original sequences, but with the gap characters placed in the right position so that the two sequences are aligned. We're going to start from the end of the sequences and the bottom right cell of the matrix. And for example, if we use this convention here, when we find a 0, we need to go up. So this means we're going to use one character from sequence 1, which is the one that we have here in the rows. We're going to use one character from this one, but since we are going up on the matrix, we are not going to use anything from sequence 2, which is at the top. That means that when we go up, we use one character from sequence 1, and we use a gap on the side of sequence 2. If we find a move of direction 1 using that convention, we need to go left, because direction 1 was when we went right. So when we're going backwards, we go left, and this means we're going to use one character from the end of sequence 2, and we're going to align it with a gap, because since we are going left on the matrix, we are not going to use anything from sequence 1. If we find a 2, then this is a diagonal, it's a match between the two sequences, so we're going to use one character for each sequence in the alignment strings here. And we're going to stop when we reach the top left cell, because this is also when we reach the beginning of the two sequence strings. Okay, so this is an example of how we can use this program after it's done. We're going to create these two strings for the alignment, and now we're going to call the global matrix function with the two strings. This S1 will be on the rows, S2 on the columns, with a gap penalty of -2, as we used before. This is the third argument that we're going to send here to the global matrix, and we're going to use that function that we built for the substitution matrix here. This function that gives us +1 if the symbols are equal, -1 otherwise. So this returns two matrices. The scores, which we can use to find the alignment score. The last cell of the scores matrix has the global alignment score. This is what we find here. And the moves matrix that allows us to trace back from the end to the beginning and create the alignment strings. So we're going to call this traceback function. It's going to create the two alignment strings here, and we can print the two alignment strings, and this would be the result. So this would be the result of aligning these two sequences. We have some gaps here in order to fit the sequences together, and this would be the global score at the end. So you can try implementing this and test with this example. Okay, so to sum up today, this was we looked at using Numpy because this is useful for several different problems that we're going to solve, and it helps you implement these alignment algorithms. And this is important because implementing the algorithm is a way of making sure that you understand exactly the algorithm in detail. So we're going to use these NumPy arrays because they allow broadcasting and indexing and so on, and make it easier to do this kind of computations. They are not as good for appending as lists, but in this case, since we can create the matrices right from the start using, for example, zeros or ones, we know how many rows and columns we need for our arrays. We can just create the matrices for this problem and then fill them with the values that we want. If you need to create a matrix after adding an unknown number of elements, then you can start by using a list, append everything to the list, and at the end you create an array using the NumPy array function to convert a list of lists into an array. But for this particular problem, we don't need to do that because we know the size of the matrices we need. If you want to learn more about NumPy, then you can take a look at this tutorial here. This is optional. It's probably going to give you more information than you need for these exercises, because the goal here is not so much to get you proficient with NumPy and Python, but to use NumPy to help simplify the implementation of these algorithms, these alignment algorithms, so that you can focus on your understanding of the bioinformatics algorithms, which is what matters for this course.